Hey everybody, I'm Mike. I'm co-founder of a startup called Wagon. We are right here in San Francisco. We're a little software engineering startup. We're just 7 people. And the team has been Haskelling for just over a year now, but I've been Haskelling since about 2010. And so the things we're going to talk about today are what's Haskell, like why bother, what's the big deal? Just a little intro there. And then to flip it around, what's Wagon? And how do we use Haskell at Wagon? So what's our architecture, loosely speaking, and why do we choose to use Haskell for it? And then I have some examples cooked up for you of great Haskell libraries that we use every day. So these are they come from the core libraries that we use at Wagon on a frequent basis. And then at the end, just a little bit of sort of the highs and lows of using using Haskell at a startup. But before we get into it, I'd love to learn a little bit about the crowd here. So how many people here write Scala for work on a regular basis? Cool. Expected as much. But how many of you write Haskell on a regular basis for work or otherwise? Oh, very cool. Very cool. Okay. And then before we get into it, a couple just little community notes. There are some Haskell meetups coming up in San Francisco that if you're into Haskell or even if you're just into Scala, maybe you'd like to come to. There's one tomorrow, December 9th at Front Row Education. Front Row is like, I'm turned around, but down market towards 6th Street. And that's December 9th tomorrow. And then there's one on January 13th at Wagon. And we're in the Mission, easy to get to, BART, the whole thing. So yeah, if you like Haskell, you should come to those things. Cool, so let's get into it. As many of you in the audience know, Haskell is a general purpose programming language. It's niche in some regards, but it is good for lots of things. And so let's talk about some of its attributes real quick. It's compiled, it's statically typed, it's lazy, and I'm going to go through and talk about what all these things mean. It's pure, it works pretty well cross-platform, and this is one where maybe I have to duck, but it's fast. And I'll try to qualify that later a little bit. So to talk through them quickly, it's a compiled language. So that means that it's not like Python. We have to send our source code through a program, and we get out a program that we can then run and do work with. That compiler is called GHC, and you might use that directly occasionally, but frequently you'll use it through some kind of a build tool. We also have an interpreter. It's kind of interpreter. It's called Run Haskell, and it just means you can take your source code and you can run it without having to go through GHC and like go through a full compile process. It's slower, but it's handy for things like scripts. And we also have a REPL. So you can see in a little bit of a command line example there, we can put some code in a file, we can compile with GHC and run the executable, just running some native code. It's nice and quick. We can sort of evaluate it with Run Haskell, and we can also hit the REPL GHCI, load our code, and kind of interact with it directly from there. If we had multiple functions in that file, we could call them separately and play around with them in GHCI. It's a handy tool. Haskell is also statically typed. This is a big part of what makes Haskell so awesome and so different from the other languages. Not that there aren't other statically typed languages, but Haskell sort of takes it to a level that most languages don't. So what that means, first of all, is that everything has a type. Ints and bools and lists of things are, of course, types. But more abstract things are also types, and also more concrete things that we might define ourselves, like a user or a database connection. We can see a little bit of that at the bottom. If you actually do open up the REPL GHCI, if you have Haskell installed on your laptop, you can ask it the type of a string expression, a string literal, and it'll tell you, this is a list of cars, which in Haskell, for better or worse, is synonymous with string. You can ask it the type of an anonymous function, and it'll tell you that it is a function from something to bool. Here we're taking x and asking whether it's greater than 5. So it's a function from something to bool where that something has to be a number and has to be orderable. Cool. You can go into more of what that means later, but those are constraints. And then just up on the right briefly, we could take a function We could apply it to a list. So we take a function from number-ish things to bools, and we map it over a list of number-ish things, and we get out a list of bools. So everything has a type at all times. You can always ask what the type of an expression is. Sometimes they won't type, and that's a compiler error. But generally, that's a very useful fact of Haskell. This one's probably the most controversial of these points. Not controversial in whether it's true, but in whether it's good. The Haskell is a lazy programming language, and that's sometimes called non-strict evaluation. That means that when we ask for a result, or rather when we construct a result, it's not necessarily computed at the time that we construct it. It's not computed until we ask for it. And if we never ask for it, it's never computed. That's handy. It means that we can work with infinite data structures, which is cool for control flow. But it also means that you define a bunch of computations and then don't evaluate them. They frequently take up a lot more space in memory in their unevaluated form than in their evaluated form. And then that can lead to space leaks. So that's kind of the two sides of the lazy evaluation model. We can see it in action here a little bit. If you ask the type of the take function, it says, give me an int and a list of something, and I'll give you another list of that something, having taken the first n elements. But we can also define an infinite list really easily just by asking Haskell to iterate from 1 without an endpoint. So that's let nums equals that bracketed expression with 1. Whoops, sorry about that. And of course, we can take the first 3, we can take the first 10, that's fine. But if we try to ask the length of that list, it never returns. Haskell will spend as long as your computer will run on trying to count the number of ints in that list. It'll eventually, I guess, roll around after overflowing. So this fact that Haskell is lazy by default, as opposed to sort of strict by default languages like Scala, it's controversial in whether or not it's a good thing. A lot of people prefer languages like Scala that are strict by default, where you have to opt into laziness at the specific points that you want it. Haskell would be very different. It would be a very different language, I think, with even a fairly different ecosystem if it were strict by default. So it is really sort of a core tenet of the language. And just sort of as a meta point on this slide, laziness is broadly applicable to a lot of things, but I think it's most useful for control flow. So if you get into using Haskell and you find yourself trying to do data processing with lazy structures, you might be in for a bad time. You might be in for extra space leaks and things like that. But treating lists like for loops and treating trees like search spaces and things like that in Haskell and letting them be infinite is a really cool way to sort of do control flow. I don't have a great example of that, so I can answer any questions on it before we go on. Okay. And in general, interrupt me, ask questions, the whole thing. Of course, we'll have time at the end. Okay, so Haskell is also pure, not in some weird religious sense, but pure in the sense of separating side effects. So pure values are safe in the sense that we know what they are. They're either already evaluated and we fully know what they are, or we know through some set of guarantees that when we do evaluate them, nothing will happen to the world, no state will be mutated, no actions will be taken. They're just values, and we can get at them if we want to. Side effects, on the other hand, like printing to a log file or running a database query, or in some other languages, even like allocating memory, those are necessary, generally speaking. We want our programs to do I/O of some kind, but they're dangerous because in general, they can do anything. So we try to separate them. And Haskell goes out of its way to help us separate them. So maybe if you're a programmer in another language without this property, you would go out of your way anyway to separate pure code from code with side effects. And Haskell just goes sort of the next step and makes it more explicit. So here we can sort of illustrate the difference between the two. We can define a string expression, a string literal. We can ask its type. Again, it's a list of cars. But we can also define an expression which isn't itself a string, it's a side effect that produces a string. So we can, in one sort of, one expression there, we can print a prompt to the command line, and we can then ask for the next line up to the new line character. And it's kind of a prompt function. And it's not itself a string, it's an IO string. So in Haskell, the most general kind of effect that you can use is called IO. If you have an expression in IO like this, the type basically doesn't tell you anything about it except what it returns. It doesn't tell you what it's going to do or what change it's going to affect in the world. It's just, this is going to touch the real world and it's going to bring back a string. There are forms of more restricted effects in Haskell. If you want to look into them, you should chase down a thing called monad transformers, and they sort of give you a more fine-grained way to touch the world. But definitely more of an advanced concept. Okay, briefly, Haskell is cross-platform. GHC supports Windows and Linux and OS X on the normal architectures. I think it also supports ARM. You can build it for iOS and some other situations. And generally, the system libraries are good about exposing cross-platform APIs. If you ever do have to build something on Windows and Mac and Linux, you'll be happy to see that FilePath, for example, has a system FilePath Windows and a system FilePath POSIX module, and it just knows at the top level module to expose the right one for whichever environment it was compiled on. So that's really handy. That smooths out most of the cross-platform issues. There are still, honestly, like a few little rough edges trying to build things on Windows. My understanding is that many of them are improved or fixed in upcoming versions of the compiler. But for the most part, it just works. A couple little edges, but it mostly just works, which is really awesome. And from the Wagon perspective, we're going to get into what exactly Wagon is in a moment here, but spoiler alert, part of it is a desktop app. And we've just recently gotten into building Wagon on Windows, and getting our Haskell code to build was honestly like the easiest part of that process. So that was hoped, but also kind of unexpected and refreshing. Okay, and then the last of my claims here is that Haskell is a fast programming language. I'm gonna say right off the bat that almost no matter what programming language you're using, naive code is almost always good enough. So this is kind of an irrelevant point in most cases. And we could put in some crazy benchmark charts on this slide, but I didn't bother. But the truth is that GHC has a lot of optimization knobs. You can write naive code and it is good enough in most cases, but there's a lot of opt-in optimizations that you can bring into your code. You can control strictness. You can control actually the memory layout of your data types, actually pretty fine-grained control there. You can implement rewrite rules for the compiler. You can sort of ad hoc the compiler a little bit that way. And there's some other ways also. And then on top of the literal optimization tuning that you can do, GHC comes with good time and space profiling tools. So when you find that nugget of code that's really needs to be a fast loop and you want to get it there are good tools for that, and they're well documented. And I wouldn't say they're the easiest thing in the world to use, but it's definitely usable. So fast is famously hard to qualify, but I'm calling it fast. It's faster than Ruby. Okay, so let's switch gears a little bit and talk about what Wagon is, so I can try to convince you that Haskell was a good fit for Wagon and that we're doing a maybe sane thing in architecture, who knows. So Wagon is a modern SQL editor, and I mean that in the sense of kind of a SQL IDE. So it's a desktop app, and it lets you do a few things. Once you've downloaded it and signed in, you can connect to your database, you can run your SQL queries, you can iterate more quickly than you would otherwise because we give you really quick sort of instant summary data. And you can also explore the results that you bring back from the database in sort of a drag and drop charting UI. So again, desktop application, it connects to your database from your laptop, not through some IT intermediated connection portal. So it's more like sort of a traditional SQL tool in that regard. But we've chosen to leverage the sort of honestly ample processing power that we have on people's laptops. We're all walking around with these 16 gig multi-gigahertz machines in our backpacks, or just carrying them around. But most of the applications we have don't individually make good use of that. And then on top of that, almost everybody has an SSD in their laptop these days, and places where that's not true is changing rapidly, and that's also much to our advantage. So I'm gonna attempt to pop out of Keynote and show you Wagon really quickly. This is like a classic thing not to do in talks. I'm gonna see if I can. I'm not on the Wi-Fi. Is this gonna be impossible to get on the guest network here? Which one should I be headed for? Apologies, guys. I should have done this beforehand.
Not this one.
Oops. No. What's it called?
Cuckoo? Using Cuckoo, right?
Cuckoo. Nice. I'm in. Cool. All right. Okay, let's see if I can drag this thing over here. I can't really see my mouse on both screens at the same time, so we'll just hope that this. Nope. You guys think you can see both ends of that window? Yeah, it looks pretty good. Okay, so here we are in Wagon. I already opened it, but if we reopened it, it would look something like this. You'd see a little loading GIF, and we'll be asked to connect to a database. And I'm gonna connect to our demo database because it's just great for this kind of thing. And we can see, maybe I have internet access. I do. Okay, so we can see some queries I was writing before. This does look like a test query, and some results that I got back. And if we'd like to, I can go over here and I can create a new query. And I can maybe with one hand write a SQL statement. Okay, so we have some baseball oriented data in our demo database. So if I went to baseball teams and remembered how to write SQL, like it's my job, then I could run a query and get an error. I can't even see that syntax error. P. Yeah, but then I'm gonna have to like unmirror it. It's not gonna be fun. Okay, so we're so close here. This is the worst job I've ever done of writing a SQL query. Okay, cool. So we got data back. If we wanted to expand that query and put other SQL stuff in it, wheres and orders and limits and things like that, we could do that. But once we've gotten this data back, we have a little summary preview of the data here, but we can go explore it in full. And this is where we start to go beyond what other sort of basic SQL tools would offer you. For one, we can sort things because we are caching data locally. And we can also pick up these sort of on-the-fly summary statistics that we've generated while the data was coming back. So this is the home, which I assume is games at home. This is summary data about baseball teams. But just the same, we could look at bats. So a nice skewed distribution of at bats by team. And if we wanted to, we could dig in and try to learn why the distribution was skewed that way, or try to justify it with other queries on the data. So we think this helps a lot in sort of iterating through the process of analysis, and being able to do this quickly and to be able to connect from the laptop is a big reason that we've sort of pushed towards this architecture that we have today. And we'll come back with an architecture diagram that sums it up in a second. Just to show you that last bit about exploring, if we wanted to actually make a chart here, we could do that with this sort of drag and drop UI. So we could put year on the dimension, and let's take our at-bats and put it in the metrics and like average it. Okay, cool. And we could make it into a table or a line graph or whatever we want. We could give it a name. We made a nice chart. So this is Wagon the SQL IDE, Wagon, the modern SQL editor. And if I can get back in here, there we go. Okay, so Wagon is also something else. It's not just a desktop app. There's a reason that we run stuff in AWS, like we'll see in a moment. It's because we also want to help people share data with their teams. So you have results in Wagon on your desktop. You'd like to share them with your team. You'd like to control the permissioning on those things because your data is important and valuable to you. And you generally like this ability to be able to view your data and for others to view your data without having the desktop app in whatever web-enabled interface they have. So that side of Wagon is, of course, a web application. It's the kind of thing where you can sign in on your phone, you can sign in on your laptop, wherever you want. It gives us a way to do centralized authentication and permissioning, like we sometimes take for granted in web apps. And of course, the other advantages of running something in the cloud or in a data center is we get scalable, durable data storage. So it means that the metadata isn't just stored on the laptop. Your query history is on our servers. You don't lose it. Your shared data is on our servers, so it's not lost if you have your laptop stolen or something like that. Cool. And then let's try it. I bet it's quicker this time. Okay, sweet. So if I jump back over here and I hit the share button, if I can reach it, it does a thing, and then it tells us there's a URL on our clipboard. If we open up Chrome, who knows what we'll see. But there's our data on the web on the wrong screen. Here it is. Okay, there it is in Chrome. I'm not gonna belabor it too much farther, but that's the flow. That's as easy as we want it to be to get your data from your laptop to someone else. Okay, so that's Wagon. It's sort of this two-ended product, and as a result, it's kind of this two-ended architecture also. So let's see, let's get into play. There we go. So Wagon architecture. This is a simplified diagram, but we can talk through the basics. And the parts that we're going to care about today are the ones in gold. At one end, we have the user's database. That's what we want the user with the desktop app to connect to. At the other end, we have our web infrastructure. It runs in AWS. It actually runs on Elastic Beanstalk, but it's really just a load balancer and EC2 underneath. It talks to S3. It talks to a Postgres database for smaller metadata. But this server component on the right, our server-side actual HTTP server, is written in Haskell. And then on, and then on the client side, the piece of the desktop app that actually talks to the database and does data processing, does local caching, handles database connections, that's written in Haskell. And we call it the database connector, or sometimes just the client. So server and client here in gold are both written in Haskell. And they're different. They're necessarily different. Our Haskell systems have different constraints and different concerns because they're running in different places. And they have different requirements. So server side, we have a lot of users, a lot of requests, and a bunch of instances of this thing all running together like you would in a normal web app. And it runs in Linux via Docker. So this is a pretty normal web app setup. The client side is very different from that, though. We only have one user at a time talking to a given instance of this thing. They're only making a few requests. It's just whatever their own instance of Wagon can generate. But this needs to build cross-platform. This needs to work on OS X and Windows and soon to be Linux as well. So that's sort of the environment of these things, of these systems. But the concerns of them are quite disjoint as well. The server-side concerns are web appy. They're authentication and permissioning, CRUD operations, just putting data in and out of Postgres, similar operations, putting bigger data in and out of S3, and doing a good job of that. But then on the client, it's all sort of application focused. We need to be able to execute queries on a lot of different database types. We need to know the difference between Postgres and MySQL, and also between MariaDB and MySQL, and MemSQL and MySQL, and Redshift and Postgres. So that's That's a big chunk of that complexity. And because we want to be able to power things like charts, we also have this ability to cache database results locally on disk. So that means data streams back from your database. It's not held onto en masse in our Haskell code. It's actually just written straight into a SQLite database on disk. So that's how we sort of hang on to the data, but not blow up our memory requirements. And then also along the way, we compute summary statistics as the data streams back, and we compute charts after the fact on demand by reading that SQLite database. So super different concerns here. But nonetheless, despite the fact that we have different constraints and concerns, we managed to get away with a quite constant set of core Haskell libraries at Wagon. Despite the fact that these systems are so different, we've managed to maintain a lot of parity between them in the libraries and the dependencies, as well as our code that we like explicitly share between them. But before I get into the specifics of these, like any questions on this stuff? Any questions on this stuff? Love to clarify any of the why or the how of it before we get into the specific Haskell end. Okay, more time later. Okay, so the kinds of core libraries we use. And I want to show you these not just because I think they're great libraries and everybody should use them, but I hope to give you a sense of how these things kind of fit together. And we'll get into some examples to that end as well. But it's kind of amazing in the Haskell world how well the core set of libraries fit together and mesh in a really snug way that libraries in other ecosystems don't always, in my experience. So at the top level here, we have a library called Y. It's an acronym. It stands for Web Application Interface. We'll come back to it for an explicit example, but it's really just a low-level, I wouldn't even really call it low-level, a minimal API to define HTTP services. So if you want to write a web framework with a lot of batteries included, you might build it on top of Y, and people have done that. Or if you want to just build a simple sort of JSON API, you might just wrap it in a little helper module and go from there. And the latter is actually what we do at Wagon. So that's super helpful. It lets us get things responding to HTTP and serving JSON. The next level down is a library called Conduit. So were some of you here for Michael Simonin's talk? Maybe like 3 weeks ago-ish? Yeah, so he talked about Conduit. He's responsible for Conduit. And Conduit, again, we'll have an example later, but it claims that it's a solution to the streaming data problem, which is a bold claim, and I believe to be true. It is a solution to the streaming data problem, but it's also just another really strong control flow abstraction. The idea being, if we can handle streaming data in some kind of uniform pattern, then that's going to simplify our code a lot. We can separate our consumers and our producers and our transformers, and then compose them ad hoc. So we'll see an example, but that's a huge part of our code base at Wagon. Resource T, I'm going to gloss over because that's my third example later, but it helps with resource handling. Resource handling is something that we all run into at some point when we're building real systems, because we have to do I/O at some point, and it usually involves a scarce resource from the system, whether it's a file handle or allocating memory or grabbing a database connection or what have you. There's only a limited number of those things available. The resource T is helpful in that sense. Parsec and its sort of parent parsec are like very famous libraries in Haskell. They are really good for writing parsers, specifically backtracking parsers. And it doesn't come up every day, but when you have a data format or a language that your code doesn't understand and you'd like it to understand it, and you probably have specific requirements about how it fails and what happens when it doesn't understand something, these libraries are really awesome sort of Swiss Army knives for dealing with text from that angle. Byte string, vector containers, just data structures in general, useful no matter what ecosystem you're in. Haskell has some really solid ones. On the server side, now we get down to these last 2 points. So the biggest difference from this perspective between our client code and our server-side code is how we manage state. And I think that's interesting that these Haskell libraries do well in these different situations, and we just sort of have to swap out in some sense, the parts where the I/O hits the real world to manage state in different ways depending on our constraints. So on the server side, we want to get things into Postgres, and we want to get things into Amazon services. So we use a library called Persistent, which does a pretty good job of being a Postgres-y ORM. And we also use a library called Amazon Ka. We have used other ones in the past, and I believe we're moving in this direction. Amazon Ka is a really cool library. It's basically Haskell code generated from the Amazon API docs. And it still manages to be usable in like a pretty Haskell-y way with I guess, a lens-based interface. So that's impressive in and of itself, I think. But it's also very useful, and it's very complete because it's built straight out of those API docs, which I believe themselves are generated. So it's like very reliable. So that's server side. Stuff goes into Postgres, stuff goes into Amazon. On the client side, it's a little different because we don't want to write things into a database that's like off the machine somewhere. We want to keep things locally. We want to put them on disk, and in some cases, we even want to keep them in memory. And we have that ability, or we have that luxury, because there's only one instance of the client running for any given user. So that means we can hold things in memory, and nothing can stomp on it. No other instance can come in and screw that up or give the user a different picture of the world, because there's only one. We just have to worry about the thing dying. Question? Stale data? What do you mean by stale data? Yeah, so the data that is cached on the client and then later shared to the server is immutable today. So it all corresponds to a single run of a query. Like you get a query result, and then that thing exists locally, and you can move it to the cloud if you choose to. But if you want to rerun it, that's a new result. And we're building mechanisms to sort of update them, but yeah. Not really, because all of our mutable data lives in Postgres on the server side. We don't maintain any user-facing mutable state on the client. We maintain the state of running queries on the database and the streaming state, like the operational state of it coming back from the database, how many rows we've gotten, how many chunks. But as far as the user is concerned, if something is in progress and the app crashes or they close the app, like it goes away. They didn't finish the query, so they'll have to rerun it. But as soon as a query is done, we persist all of its state to the server, and then it's there forever. We try to partition these things for that reason, because we wanted to avoid these kind of stale or essentially caching problems. Okay, so the libraries we use on the client side to help with this stuff are STM, stands for Software Transactional Memory. I think Michael talked about this in his talk, but it's an amazing thing. It just kind of like falls out of Haskell in a way that has been in the past very difficult to implement in other languages. So we get this really awesome concurrency abstraction of STM almost for free. Async is a sort of a thread management library, which helps a lot when you need to fork off a process and then poll against its state, or you want it to publish its state to another piece of code. And SQLite, I mentioned, we put the data explicitly into SQLite, and it lives there as long as we choose to keep it in cache. It's just a convenient, fast read-write sort of row-based data store. Okay, so those are among our most useful libraries in Haskell. I'm going to go and do examples of why conduit and resource T. And I think the three of them make a nice triplet, because you can really see how Haskell libraries start to mesh together. So let's get into that. Okay, so here's why. Like I said, why is a minimal API for writing HTTP services. If you've come from the Python world and seen WSGI, or if you've come from the Ruby world and seen Rack, it's similar, pretty similar to those things, fits in the same niche, in the sense that it's not a web server, and it's not a web framework. It's just sort of a middle layer that determines how those things should see each other. It's an interface. And in the spirit of being simple, it has a single central type called an application. And I want to talk through what this type means and why it looks the way it looks. So in Haskell, when we write type something equals, this is just a type synonym. There's no special constructor for this. So all we're talking about here is a function. Application is a synonym for a function from request to this kind of meaty thing in the parentheses here. And then the result is the result of that meaty thing. So I'm going to call the first argument request. I want to call the second argument respond. Because what it is a responder function. It's a function that our application gets as an argument that says, give me a response, and I'm going to give you a value denoting that I sent it, roughly. And then the contract of the application is just that it has to return that confirmation value at the end. Does that make sense? That we have this, in some sense, we're being passed a continuation function here, and we're going to call that continuation function when we have a value that we'd like to send back to the user. Okay. So then the place where the rubber really hits the road here is with the request and the response types. We don't need to be able to construct requests because from the application writer standpoint, the web server is going to do it for us. In our application type here, request is an argument. It's the first argument. So it's going to be constructed for us. And similarly, we don't generally, unless we're getting really deep into it, and we'll see some of it on the next slide, but generally we don't need to be able to deconstruct responses either because of sort of the opposite reason. We are constructing them. We can construct them in whatever format we want. So then that means that sort of motivates why the API looks the way it does. It includes a bunch of functions for deconstructing requests, getting the path info, asking for request headers, getting the body of the request. These are all things we can do given a request. But we don't have any request constructors. And then on the other side, we have these response constructors. We can, for example, build a response from a file on disk. We can just give it a file path. And it's the web server's responsibility to return a 404 if the file's not there. And similarly, we could give it a byte string directly if we just have the data in memory or in our program somehow that we want to return as our HTTP response. We can just pass it off that way. But no super thorough ways to deconstruct a response in the top-level API. Okay, so I think that's enough to convince you that we can build functions of this type. But I want to note here that we don't really have to care about response received. We don't need to know how to deconstruct it or construct it. It's helpful to know that we're handling a value of that type, but otherwise we don't really have to care about it because we have this continuation function that is going to give us a response received, and the only contract we care about is that we have to give it back at the end. So you see this type pop up roughly one place in the top-level API of Y, and it doesn't show up anywhere else, and that's fine. Okay, so that's application, request, and response. Let's build a little application or read through one. So this is a simple Hello World app, not using a web framework or anything like that, just pattern matching on the path info of a request to produce one of these application functions. So Hello app takes those two args, the request and the respond function, pattern matches. If it's /hello, okay, respond 200, say hello world, otherwise respond 404, say not found. So this is sort of the bare bones of actually building web applications with this thing. Now, of course, this doesn't have a web server. You need a handler. Y has a number of handlers in the world that are all on Hackage, but the one that you actually want to use is called Warp. Warp is a really solid web server built basically behind the Y abstraction. And it does all kinds of stuff. It supports HTTP2. It has good streaming support. It knows what to do when things go wrong in the file system. And it works on Windows, which is great. Okay, so that's a simple one. And now the last thing I want to show you about Y before we move on to Conduit is this thing called middleware. Now, middleware is a little trickier, but it's really powerful and I think sometimes underused in this ecosystem. So before well, I guess it's intuitive, right? Sort of what middleware means. It means we want to put something between the actual web server endpoint and our code. We want something to either screen requests or change them in some way or change them on the way out. And we can do that with this middleware by expressing it as a function from an application to an application. So just to show you how powerful and brief it can be, let's implement the skeleton of a CORS middleware. We use CORS in a couple places at Wagon because we have these components kind of sitting all over the place on all kinds of different environments, and it's helpful. But the basic tenet of CORS is we want to handle pre-flight requests. How many people in the room have had to deal with CORS before, have seen a CORS error? Yeah, they pop up in web apps once in a while. So CORS stands for cross-origin resource sharing. And it's an agreed upon scheme whereby we put some new headers on our requests. We expect some new headers back from a server. And in the case of anything but a GET request over HTTP, we have to send a pre-flight. Pre-flight being an options request, like one of the weirder HTTP methods. So a CORS app is going to send a pre-flight request for any non-GET request beforehand. So we can see that logic here. Our function, or rather our middleware, CORS mware, you can see that it is an application to application. It is an application in that it takes a request and a responder, and then it takes another application as an argument. And it inspects the request. It says, is this a pre-flight? That's just a simple predicate. We could define it down below, but it's omitted. If it's a pre-flight, if it's a pre-flight, we handle that. And handle pre-flight is just an application that we've composed in here. We passed it the same request and response, or request and responder function that we were passed in at the start. And then if it's not a pre-flight request, we pass control off to the inner app. This app here on the fourth line of CORS mware, that's the app that was passed into our middleware. It's the first argument in the middleware type. So that's the inner application in some sense. And we're going to pass control off to that. We're going to give it the request. And we're going to give it a slightly updated, slightly wrapped up respond function. We have this respond CORS function that has a type at the bottom. And it's also nicely straightforward. The type looks like any other respond function. It takes a response and returns an IO response received. And it's just adding, I can't click over here. It's just adding CORS headers, which is all we have to do. So we just compose that in, we pass the inner application, that respond function, and kind of awesomely, like suddenly we have a CORS supported server, which is finicky and edge casey if you try to do this imperatively. Questions here about how these things fit together? Because aside from, well, honestly, like things like Finagle, I haven't seen a lot of situations where you can compose HTTP services in this way, where you can wrap them and nest them and sequence them as needed based on predicates. It's very powerful, and we use it in a bunch of ways at Wagon to get sort of higher leverage out of less dev time. It is, yeah. That's passed in as almost like a dependency injection kind of thing. Yeah, it handles that and sends the data out on the wire, like a web server. Okay, cool. So that's why. That's what I'd like to show you about that. It's a powerful little library, and a lot of the sort of web services Haskell ecosystem is built on top of it. The web framework Yasad is built on top of it. Some of the micro frameworks are also built on top of Y. So it gets a lot of mileage. The next thing I want to show you is Conduit. I know that Michael talked about Conduit a little bit in his talk, so I'm going to take a little bit of a different angle on it. Like I mentioned earlier, the Conduit docs say right at the top that Conduit is a solution to the streaming data problem. So let's talk a little bit about streaming data and what the problem is. So streaming is, you can come to it from a lot of angles. If you don't like my definition, it's okay. But the definition of streaming I'm going to use is that it's this proposition that we can handle more data with less latency, at least per unit, with less computing power. The idea being, if we don't have to hold all the data in memory, if we can process it as a sequence of chunks or of some other unit, then we don't need a 100 gigabyte memory computer to handle a 100 gigabyte file. Maybe we only need a 50 megabyte memory computer to handle a very large file, because it can take its sweet time handling each chunk of data. And nonetheless, it can be quicker on each chunk, certainly, than a big computer would be handling the whole thing at once. So that's what I mean by more data, less latency, and less computer. So Y that we just looked at, we'll hark back to it a little bit, has some basic streaming abstractions. Because of course, sometimes you have really big HTTP request bodies, or you want to send really big data back as part of an HTTP response. So this is what it looks like if you want to construct a streaming HTTP response directly with Y. It's a little hairy and a little low level, so we'll take a sec here. For one thing, I got this example a little wrong. That shouldn't say response file, that should say response stream. I'll fix that before we put the slides up. But response stream would take a status and a list of headers like the other constructors. And then instead of taking a raw byte string or a file path, it's going to take a streaming body. Streaming body is just another type synonym for a function. Here it is down here, just to the right. And it's a function that is passed a send function and a flush function. These are, again, continuations, kind of in the style of the application type. So if we're going to make a streaming body, we need to write a function that takes send and it takes flush, and it does something with them. It sends data until it's done sending. It flushes the pipe along the way whenever it wants to. And then when it's done, it just returns unit. And that's how we would produce this arbitrary stream of data for Y. This is cool. It's low level, and there's like honestly something satisfying about programming at this level occasionally. But it's difficult to work with at scale. And when I say scale, I mean scale of complexity and scale of code base. We wind up in sort of hard to compose middle ground, because I don't have it here, but this is roughly what it looks like to implement a consumer. If you wanted to implement a producer, this is what it looks like to implement a producer. If you wanted to implement a consumer, you would have a similar looking set of types, and one of them would be receive instead of send. Okay, cool. Okay, so that's response stream. It's hard to compose. We can't really glue it together with a consumer or define a transformer easily. It's very imperative to use. So Conduit moves away from that. It says we should be able to compose our streaming components really easily. So for the sake of the talk, and because I'm a little short on time, I want you to, as best as possible, ignore the types to the right side of the equals there. Look at the left side and see that we have producers, conduits, and consumers. And they're parameterized on their input, output, and result types. So producers have an output type O. Conduits, which are just transformers, have an input and an output type. Consumers, which take input and produce a result, have, accordingly, an input type and a result type. Sorry, I'm not sure I'm always speaking to the mic. And then the trick here, of course, which I'm going to gloss over, is that they're all implemented as type synonyms over some underlying type. It happens to be called conduit M, and that fact lets us compose them really nicely. So I'll leave it as something to dig into after the fact. We have this fuse operator. It's defined over that conduit M type. If you've seen the type of a composition operator before, then this kind of makes sense, because we put in something that's sort of A to B and something that's B to C, and we get something that's A to C with the added wrinkle of this result type. So this is useful because it roughly gives us a kind of inversion of control for handling I/O. So here's a simple file copier. We could build a producer that takes a handle, produces byte strings, We could build a consumer that takes a handle, consumes byte strings, produces no value at the end, and we could use that to copy files around, and it works great. And if we read file and write file, well, it happens in constant memory and has all kinds of nice properties that emerge in some sense from the properties of the components. It's very handy. So that's all well and good. That's conduit. But if we never had to do I/O, then conduit would be total overkill. If we never had to do I/O, we would just use lists, and we would use map and fold as our conduits and our consumers, and all would be fine because we'd always be dealing with pure values. Everything would always be in memory or generated somehow. But that's not true. We care quite a bit about I/O, and so we have a library that helps us deal with it. It's called resource T. The main issue is that data does involve I/O for the most part, and the root of it is that resources are scarce. We have to care for them. So if we're opening a file, that's a file handle. If we're allocating memory, it's that pointer in some other language that's not garbage collected. If we're talking to a database, the connection itself is a resource. Lots of bigger enterprise-y databases for analytics limit the number of connections you can have. So you want to clean them up. Similarly, if you're already connected to a database, you might have a limit on the number of transactions you can start. So all scarce resources. To breeze through this, lots of languages have scope resources. I don't exactly know what it looks like in Scala, but in Java there's try finally, or try with resources finally. And in Ruby we have blocks, in JavaScript we have callbacks. The basic pattern is the same, is that we want to get a resource, and then even if there's an exception, we want to make sure it gets cleaned up, given some predefined cleanup operation. Haskell has this. It has scope resources. If you've ever done I/O in Haskell, you may have run across bracket. Without getting super deep into the type, you give it an action to acquire the resource, a function to release it, and then the actual function you wish to use to do work. And we can invoke it in as many nested forms as we want. So here over there, we're doing the same thing we did on the prior slide. We are opening a file, we are opening another file for output, and then we're running our conduit. So whereas that thing we saw over there needed file handles, didn't actually deal with the resources, I just skated over that. This one actually deals in file paths and can take care of itself. So that's cool. We get basic nested resources. We haven't even come to resource T. Resource T, for one thing, in its basic usage, flattens out bracket. So if you're dealing with a lot of nested resources, I've taken up their time. Okay, sorry. We'll be 3 more slides, quick ones. Okay, so resource T flattens bracket. It means we don't have to have these nested things. It gives us a way to roughly not have to nest. We get to keep sort of hidden context of our resources, and then they're all cleaned up automatically at the end. And it also works directly with conduit, which is cool. I'm going to gloss over that because it gets to the point of interleaved resources. The thing you can't do with bracket, the thing you can't do with nested resources or easily in Java or Ruby at all, is interleaved resources. So if you want to, and this is a deeper example of it, but if you wanted to open an arbitrary number of files and then write them into a sequence of files of known chunk sizes, you couldn't do that correctly without closing your file handles between opening other ones and closing those. You'd have this interleaved situation. And resource T is roughly a tool to solve that kind of a problem. It lets us embed resource allocation on our streaming components. Super great. Last slide, startup Haskell. We're a startup, so we do things a little bit differently, but I think this is good general advice. Lean on the tooling, use GHC to its fullest potential, use the types as best you can. Lean on GHCI, the profiler, and stack. The learning curve is steep. Everybody talks about this. It's hard at first for people who haven't Haskell before, but invest in their time because it's very productive and gradual after that. Evaluate libraries, avoid time sinks. That's, I guess, just normal dependency hygiene. Write tests when your types feel shaky. Don't get dogmatic about it either way. You'll know it when you see it. And shape your prototypes. Refactoring is so cheap in Haskell compared to other worlds. Cool. That's it.